right, so today we're reviewing for the test. I have a few slides prepared as discussion points, but we can take questions that you have. We can mix it up. You could ask me some questions. I could ask you some questions. Off the bat, any questions people have, I could file it away and see if we could filter it in, or topics that are of some concern. Someone on the Piazza asked for some random foresting boosting. We could discuss that a little bit. Okay. So. All right, so if there's no questions, I put, okay, so first of all, what's on the exam? It's primarily focused on the materials that we've covered so far that weren't on the first exam. That's the focus. So up to and including yesterday's discussion. Basically, you should know likelihood and how to make an objective function where you have maximum likelihood on some data. I think this is something that most of you already knew but coming in. And anyway, we talked about it yesterday, so that'll be kind of fair game for the test. Okay. All right, so I think the first topic we did that wasn't on the last test was kernels. So I just jotted down, when you think of kernels, you should definitely understand what we mean by the kernel trick. Can anyone paraphrase the idea of the kernel trick? Or want to try it out? All right. So, suppose you have a machine learning algorithm, and you can write your objective function purely in terms of what? Okay, very good. Inner products of your inputs x or of some feature mapped inputs x into some feature space. So whenever you have an x in your objective function, it's in the form of xi transpose xj, or inner product of xi and xj. It's never just a plain xi sitting there. Okay. All right, so what happens when you've written your objective function in this form, in a kernelized form? That form would be kernelized. Then the kernel trick is yeah, you could swap out that inner product. So we have just, if you write xi transpose xj, that's the standard Euclidean inner product. You can swap that out and replace it with any other inner product you want. Okay. So we've basically spoken about two ways to come up with a new inner product. So suppose we have xi transpose xj. So the first thing we can do, and we can always do this, is replace it by a new feature mapping. So it could be like phi of xi, phi of xj transpose. Okay? Now it's often convenient when we have it in this form to write this in terms of what we call kernel functions. So we could write that this is equal to k. What do I want to write here? It's two arguments. xi, right, and xj. So the kernel function takes arguments in the input space x. So kernel maps from input space x to input space elements into reals. All right? So x may not be RD at all. X could be any kind of space we want. But the output of the kernel is reals. Similarly, feature map takes a an arbitrary element of an input space. It could be any kind of input space. And it maps it to something in RD or R something. OK, so yeah, so the two ways to make a kernel function. One is to come up with a feature map you like, a new feature map, and just use the standard Euclidean inner product. And another way is to just write down a function and prove that it has the properties that a kernel function needs to have, essentially that are basically derived from inner product properties. All right. Any questions on kernel stuff? All right. Trees. So I just picked one random property that you should know about trees. Trees don't care about the specific values for a particular feature. They only care about the relative ordering of the values, right? So if I ask a question, here's in the input space, we have a feature that's temperature degrees Celsius. And someone suggests a log transform for some reason. You should realize that has no impact whatsoever on what a tree does, because the tree doesn't care about it doesn't change the relative value, so it doesn't matter. OK. What else is what else is interesting about trees, or questions about trees? So trees partition your input space, right? Every little part of the input space corresponds to a leaf of the tree. It has its own prediction. What else? What about the trick about taking the leaf nodes, the indicator functions, to say which leaf node or which partition of the input space the input's in, and using that as a feature in some other classifier? Remember that idea? So we could run a tree on some data set, and then we could take all of the regions of the space that the tree divides the input space into, and code those up as features for the data, and then run it through like Lasso or something. All right, how about bagging? True, false question. What, you have a question?
No, I didn't understand what you just said. Leaf nodes as features.
What does that mean, leaf nodes as features? Probably half the class is like, glad you asked. All right. Input space X. All right. Tree makes splits. Let's suppose there's two features. So the first split, maybe it makes here. And the next split to the left, it puts here. And the next split to the right, it puts here. And then we're bored, so we stop building our tree. All right? And we have a prediction here, A1, and here, A2. Do you know what I mean by each of these regions corresponds to a leaf node of the tree? Yeah. OK. So this is a region. And I claim that you can code up a function of x. So x maps to something that's 1 if x is in this region and 0 otherwise. Suppose this split is at, suppose this is W0, and this is W1. Then we can map x to indicator function. So this is the x1 axis, or rather call this the x1 axis, and this is the x2 axis. Then we could say x1, what would I say to, suppose, yeah. What would I say to get this region to be 1? Okay, x1 is less than or equal to w0, and x2 is less than or equal to w1. All right, so this is a feature mapping. This gives you one feature of x. And it's 1 whenever x lives in this area, and it's 0 otherwise. Okay. And we can make another such feature for each of these regions. So this is a nonlinear feature mapping of x. It represents x in a way that we can now make prediction functions that you could never produce with just linear regression. Suppose you tried to make a linear function of x1 and x2. Well, then we're only going to be able to do things like this or like this. But if we take these feature functions and do linear regression on them, we could get these types of boundaries. Yeah?
What would the benefit be?
The benefit of this is, so it's, OK, so why would you use this? Suppose you have a whole lot of data. So much data that you need something that can run very fast over the data. The algorithms that can run very fast are generally linear algorithms. Ridge regression, lasso regression, these things. Trees are much slower. Gradient boosting, much slower. OK. So we could either go linear and use all of our data, or go nonlinear and just use a subset, or wait forever. OK, well, how about this? What if we go nonlinear on a subset of data, then extract from that nonlinear thing some new features that are nonlinear features, like these things. Now take the nonlinear features as input to our linear model, and now we can run on all the data, but the final prediction function is nonlinear. It's a good question. So the question is this, can we think of this as boosting in any way? Let me think about that for a second. I don't know. Boosting is really like you build one model and then you see where things didn't do well and you build another one. It is two-stage, and boosting is multiple stages, but I'm not sure it goes deeper than that. OK, what if maybe there's some connection in the sense of if our weak learners were like single decision stumps and then we combine them with linear combinations and add a boost, and then your decision regions maybe look a little bit similar, but I don't think it's a very close connection. Yeah?
Is this like a linear model or a non-linear model?
It's close. We have a nonlinear model from which we extract an idea for feature map, for the new feature map, and then the feature map is used in the linear model, yeah. Yeah?
But since trees have high bias, is there a way to use multiple training sets or something in order to get these?
I'm not so worried about, well, OK, so I don't worry too much about trees overfitting too badly, because what I'm going to do is I'm going to take those features and then put it into a linear model that I know how to regularize well. So I use L1 regularization and a holdout set to make sure I'm not overfitting. So I'm not too worried about if the tree is going to overfit a bit. But did you have a specific idea?
No, I mean, I'm using a single tree to determine which features may be important or not. So maybe that's biased towards the specific trees that I'm using.
You mean because it's a random subset? Yeah, I understand what you're saying. You're saying that, boy, the leaf nodes of this tree, they're based on, first, they're based on a random subset of data, and if I had a new random subset, it'd be very different. And this is all true. But it's, the ones that are really important hopefully will show up for most of the trees or something. Yeah.
Does it have a relation with kernel? Because it seems that you are trying to build a new set of features.
That's interesting. Is there a direct connection to kernels? Because in kernels, we're kind of making something like a new feature map. Well, in a certain sense that for kernels, I was saying, oh, take your xi's transpose and swap in a new feature map. But maybe just to that extent. But it is about generating new features. Yeah. Learning the structure of the data. I don't know exactly what that means.
Like, when the first step in, like, when you start learning something, you want to see whether it's something that you can use to set the data sets, like visualization. Is this like some roundabout way to do that?
I don't know. I mean, it's not visualizing the data because I drew it in 2 dimensions, but generally it's going to be very high dimensional, potentially. So it's not really something you could visualize. But in the rough sense of, I'm letting the tree take a first cut at the data on a subset of data, and then I'm kind of extracting something from that, then I guess, yeah. Cool. Good mileage out of that bullet. Oh, we didn't ask the question yet. That was all trees. So, all right, so bagging. Remember what bagging is? We have our data set. It's of size n. We take a sample with replacement, traditionally of size n, although there's a really good discussion on Piazza, if you saw it, on whether we really need to keep it at n or it could be smaller or bigger. But standard bagging is you take a sample with replacement. It's called a bootstrap sample. And you train a model on that random sample with replacement. And you take another sample of size n, and you train another model, and another one. And you do that until you get bored. And then your predictions are the average of the predictions of each of those models. And the idea is that it decreases the variance and kind of smooths out your prediction, and generally helps in different situations. So, to the question on the slide. True, false. In bagging, as we increase the number of bootstrap samples, we expect overfitting to decrease. Very confusing. So if you do that resampling thing, and you keep adding more and more prediction functions to your ensemble that you're just going to take the straight average of, would you expect adding more functions will that maybe lead to overfitting, or make overfitting less likely? It's true? It's true, false. So true means we think that it's good to keep adding more functions to it. If you keep adding more functions to this average, it's not going to overfit as much. Say again? You think if we take it infinitely, are we? I don't see that. Oh, I'm not quite sure I follow either of those things. Can you ask the question again, please? Or make the statement again? Why do you think it will start overfitting after a certain number of iterations? I can't hear. A second. But after a certain number of iterations, we would be again using the same point size. It may be possibly the same sample is used again and again. So the worry is that we may eventually be getting the same sample more than once. Why is that an issue? So we have the same prediction function more than once. and so it enters into the average more than once. But we're not actually, I don't see that as being an issue. Sure, I see that. Yeah.
I was thinking that when you take a random sample, it's like you're taking a sample from the population. And the more times you do that, the more representative of the population you get.
Okay, so we're taking a sample of the same size every time, and then we're averaging the results. So it's not entirely clear to me that it's becoming more representative. Oh, you think because it's converging to the expected value or something? So here's the issue with this, is that there's no, I don't have a precise theorem about this. I'm not sure there is one. There maybe is one, but couldn't track one down. Not in textbooks, not in papers. So it's more of a, in practice it bears out, and intuitively it makes a lot of sense. Yeah? No question?
The answer is true.
Yes.
So let's say if you take bootstrap, like your data is not going to change. You keep taking bootstrap from the same data.
Yeah.
So let's say if your data is only made of one row, you can take as many samples as you want. You will always predict the same thing. So it still depends on the data. And like to reduce overfitting, for example, you want to influence on the tree depth or stuff like this. But I don't see how taking more samples, will prevent you from overfitting, because you're still taking the same amount of data. And basically, for example,
Oh wait, can I rephrase the question? Can I just change it from we expect overfitting to not get worse? So
I think it wouldn't change anything, right?
you think it won't change anything?
Like I don't see how the number of bootstrap is going to influence on overfitting or not. Right? I would say it has no influence.
You don't like the whole argument of variance decreases when you take an average of prediction functions? I found it very compelling. So we have a bunch of prediction functions, and the expected prediction is, say, the right thing, but there's variability due to randomness in the sample. And when we average those things together, we expect the variability of the predictions to decrease, but the bias should be the same because all the samples are IID. So the intuitive explanation for bagging is that the variance of the predictions decreases, but the bias stays the same. So yeah.
Decreasing bias means decreasing
in this case, decreasing variance decreases overfitting.
So why is that?
Why does decreasing variance? Decreasing variance?
Because if your prediction function is actually just an overfitting function, and you're trying to decrease the variance of the prediction, and you're just getting a new overfitting prediction. Because if all of your prediction for every sample size is overfitting, then you're just trying to get the most likely one. But no.
Wait, hold on. So all right, let's consider the prediction on a single input x. We'll just focus on this. So we draw some random data, and we build our model on it, and let's call that F1, okay? F1. And then we'll evaluate it on x. So that's equal to y1. Now, this was based on a random sample of data. And so we could also talk about the expected value of f1 of x. And let's call that, I don't know, y1. No, let's call that y star, y1 star. Okay, fine. So now we have another one, y2, which is, first of all, in this expectation, what's random? Always a good question to ask.
Data.
What is?
The input data?
The sample that we took, the training data for F. So in this, what is random? What should I underline to be the random thing? What is it? Whoa, universally incorrect. Guess again. F is random. Why is F random?
It's a guess.
That's good. All right, keep thinking. We need a reason. Why would F be random? Yes? F is the prediction function that is built from the random sample of data. X I fixed at the beginning. I chose an input X. I said, let's focus on, X equals this picture. And then every time we draw a bootstrap sample of training data, we get a new F. So F is random in this way. OK, fine. So now we draw another thing and we get another F. We got another F because F is random. And every time we draw a new bootstrap sample, we get a new F. And I'm keeping X the same every time. OK, what's the expected value of F2 of X? It's also one star. And the and the expected value of all the F's, every F that we generate randomly is going to have the same expected value. Fine. But what about when we average these all together? The expected value of this thing? Still the same. But what about the variance of this thing? This reduced by how much? Or how much did the variance just went down by, we want to do, this is the average. So the variance of the average. Yeah. OK, you can work out variance of averages. It's 1 over m, yeah.
The expected value is equal if F's are unbiased, but if...
No, wait.
Oh, okay.
The sample, the training data that I drew for F every sample is generated in the same way. So they're IID samples of training data. So, all right, so you want to say if F is on, I didn't say that F is getting the right value for Y. I said it's getting a particular value for Y.
Okay.
This could still be biased.
Okay.
So it doesn't reduce the bias, but it doesn't change the bias.
Okay.
But it changes the variance. Yes?
I could see that the variance decrease, but why when your variance decrease and your decrease overfitting? I don't see the connection between this kind of.
Well, all right, let's forget the word overfitting, because as I've kind of said, overfitting is not very well defined. Let's just say make better predictions. Can we say that? That's what I want to claim.
No, but if all of your F is overfitting, you're just trying to get the average overfitting point. I mean, overfitting is more depend on what your learner is, but not this kind of thing. Because if your learner is just an overfitting learner, for example, you have more iterations, so that every F, F1X, FMX, they're all overfitting, then you're just trying to get the average point of all your predictions, which is also overfitting.
Why is the average of something that's overfitting? I don't agree with that statement. I claim that it will fit better
that
because.
Is my question. Why you combine
because
things together, you can get a better one.
So we have an overfitting situation, right? We have a tree that fits too well, but but it's not biased one way or the other, perhaps. So the expected value is still the right thing, but sometimes it gets confused and it focuses too much on the wrong thing. Whatever, it has any particular instance will have some error because of overfitting. But if we average a bunch of those together, it's still unbiased, but the variance has gone down. So
can I say I could see that the average of all these things can be better than some of the FX, but maybe worse than some of them. You cannot say that the average is better than all of them. I couldn't say it.
I can't say anything precisely. This is this is precise, but this is not about This is not even about this. This is the thing we would actually use for prediction.
Yeah.
And what I'm saying is I'm giving you something about the variance
Yeah.
of this as a random variable, as a random entity. And we only get one of these. So I'm saying the variance of this thing is reduced. But in practice, we only have one instance of this average. And so in general, we expect it to be.
But what average is better?
Y is average.
Better than one of them. I couldn't see it.
All right, how about this? Suppose the variance of f1x is 100, okay? And the expected value is 0, all right? Okay, and I don't even know what the true value is, doesn't matter. So I generate a random f, and it predicts, what would be a typical prediction f1 of x, for a randomly drawn f1 of x? That would be the expected prediction. 0 is possible, but unlikely. What would be, it may deviate from 0 by some amount. Roughly how much? 10. So a randomly drawn f will deviate from 0 by about 10. All right, so it may predict, maybe this is 6, maybe the next one is -5. All right? So if the true value really were 0, if this were unbiased, then this would be the typical error of each of these predictions. Okay. Now, what if we took the average of 2 of them, even? What if we took an average of 10 of these? Would you expect that the typical deviation from the expected value would decrease?
Yeah.
That's the point. So, and that deviation is the error.
But there's still cannot answer the question about our opinion. I mean.
Okay, let's continue on and let's talk about this on Piazza. It's maybe too much on this one question. I mean, by overfitting, so yeah, I should have asked instead, would you expect the fit to improve? Instead of overfitting. Overfitting is not a very well-defined term. Okay. All right, so with bagging, how can we get an estimate of test performance while still using all our data for training? Say again? Yeah, this out-of-bag method. So in every round of bagging, we take a bootstrap sample and some fraction, roughly, remember how much percent? 30. Yeah, 30-something percent, like 1/e-ish, isn't sampled. And so those things are out of sample for that particular prediction function. So anytime, so you can use those points as test data for any ensemble involving this particular function that wasn't trained on those things.
You take a bootstrap of the output sample, or you just take all the points of the output sample?
So basically what you do is you take, so here's your original sample, your original data. And you take one point of it, and you look at all of the functions that were generated without using that point as training data. And you average those together, and you see how it does on this point. And that's like an out-of-sample assessment of how your thing will do on this one point. And you can do that for each of the points. So that's worth reviewing. OK. True, false. Random forest is just bagging with trees. OK, what's the extra piece?
Each time you make a split, you have to pick a random sample of the features.
OK. Each time you make your split, you're choosing among a random subset of features. Typical numbers, typical fraction for that number of features. Sometimes you use square root of a number of features, sometimes you use half the number of features. That's a tuning parameter. OK. Skip. Well, I will say that, so the inventor of the method claims very strenuously in his paper, without proof, that random forest never overfits. And what he has in mind is this thing that bagging doesn't overfit. And anyway. No, this is false. Or undecided if you only want to believe what's proved, because we haven't proved it. But anyway. Okay, add a boost. True, false. We can use regression trees as the base classifier for add a boost. No, we cannot. What do we need to use it? What's the one crucial requirement for using add a boost in practice? Okay, so there's two things. So we need it to output, it has to be a hard classifier, -1 or 1. That's really built into the algorithm. Now there's also this theorem about converging to the optimal, to like the best possible on the training set, but and to do that theorem required that it be a weak classifier to do better than 50%. I would say, but in reality, in practice, you have no idea if you have a weak classifier. This is not something that you can know. You hope, but you don't know. So that's more on the theory side. On the practical side, we need the base classifier to give hard classifications, -1 or 1. We can use SVM as a base classifier for add a boost. True, false. True, maybe. How would we use an SVM for a base classifier? Take the sign. Right, because so the SVM kind of naturally returns a score, a real number, and then take the sign. Yeah, if you want to be really careful, so sign of 0 is 0 traditionally. So if you want to be really careful, you got to make sure you map the 0 to something. But yeah, this is good. With the discussion we just had, yes. This wouldn't be a test question because it's too ambiguous, but you have to, if you take your SVM output and you convert it to -1 or 1, then yes. We can view add a boost as a method for minimizing exponential loss using forward stage-wise additive modeling. What? Yeah, this is true. This is the homework problem, and mentioned in lecture certainly. And what are some issues with exponential loss? No sparsity. This is true. I don't know. That's not necessarily an issue. It's not an issue for me. Some people complain about that. I don't mind that. Yeah. So one issue is that it penalizes incorrect answers very heavily. And so it's going to be very well affected. It's going to be heavily affected by outliers or noisy data. Okay, gradient boosting. So we've had homework on gradient boosting, right? So definitely rehearse gradient boosting. Why? Because it's easy to give problems on gradient boosting. So you should. I would prepare for that. So what does that mean? It means here's a loss function. Maybe I'll tell you what ingredients do you need to do gradient boosting? Like if I say program up this gradient boosting algorithm, you'll say, okay, I need to know X and Y. What do I need to tell you to? You need a loss function for gradient boosting, and you need something else. Yeah. Yes, you need a base hypothesis space. Okay, good. And what kind of, or a base learner that chooses from the hypothesis space, and what kind of hypothesis space does it need to be, or what kind of learner does it need to be? For the version of gradient boosting we discussed.
It has to be a vector space?
So the hypothesis space should be, okay, let's back up for a second. Hypothesis space contains decision functions. And the decision functions take an input and produce some kind of output. What kind of output should these decision functions produce? For a real value, that's right. And real things that produce real values, these are regression functions. So our black box method needs to be a regression. Good.
The black box regression is basically on times of space.
Yes, that's right. Any questions on this? Okay.
Sorry, main regression function for the ages.
What?
The functions we call age.
Okay, go on.
Those had to be the regression functions or our hypothesis.
I really can't remember H anymore, but so in gradient boosting we come up with a vector which would be the unconstrained gradient, and we got to project it back into our weak hypothesis space, and we do that. And a projection is minimizing L2 distance, so we do that by finding a function in our hypothesis space that gives predictions that are close in L2. That's just regression.
All right, yeah, and those functions were, we called them.
Okay. I'm not sure. Alrighty. Good. Multi-class classification. You should know what the ingredients are and be comfortable with them. So we have this class-sensitive loss function. You know, if I predict 3, but it's actually 4, that could be give you loss of 2. If I predict 2 and it's actually 3, or whichever was the other way around, it could be a loss of 5. There's this notion of a class-sensitive loss function. You would draw it as like as a table, right? So A for action, the prediction, and Y for truth. 0, 1, 2, 0, 1, 2. We'd have a loss in each of these 9 cells. Typically, you'd expect the loss for the correct answer to be 0. So this would be typical, 0, 0, 0. You could have 5 here, and this could be 3 here. It doesn't have to be symmetric. So this is delta. We have our feature map, which in the multi-class case takes an x and a y. And you think of it as like encoding the compatibility between x and y. And then we have our linear score function, which is a single number scoring how compatible x is with y. This is linear. We only talked about linear multi-class. And how do you write that? Your final prediction function is you take the thing with the biggest score. All right. We talked about 2 loss functions, actually. Only one on the day, which is the multi-class hinge loss, and you have this homework on it right now. So you should be pretty getting familiar with that. Any questions on that? All right, well. It's also a thing we talked about yesterday, the multinomial logistic regression loss, which is also a multi-class loss function. And this would be, you could think about this as you could either maximize the likelihood given by the multinomial logistic or minimize the negative log likelihood. But this is another loss function we can use for multi-class. So yeah, I would recommend from yesterday to go through, I had maybe 4 examples of conditional likelihood things. We went over 2. We went over binomial, multinomial. In the same slides, there's an example for Poisson regression and Gaussian regression. I think I talked about Poisson too. And I think that will get you the hang of it. I always think about it like this. We have some parametric family. With, say, parameter theta. And our model takes an x for input. First, we map it down to a single number, right? With our linear method, it becomes that. And then finally, we want to map it into theta. And theta may have some restricted range, right? So we might have theta in 0, 1. We might have theta in 0, infinity. So this gets mapped to f of w transpose x, which we take to be theta. All right.
But
Yes?
these won't be included in the exam, right?
You don't want them to be on the exam?
You said
I said that yesterday?
last week. You said that you know last week.
I said that yesterday?
Yeah.
Man, I changed my mind. Sorry, yeah.
What if the function has more than one parameter?
Great question. Love that question. So this is like not covered in any textbook I've ever seen, except in one example, multinomial logistic regression, which I did on the slides. But I would love to have a write-up that talks about more than one parameter, but I have not seen it. Good question. All right.
What's the problem if you have more than one parameter?
Well, so it's not a problem. I've just never seen anyone give an example of it. So what would we do in that case? We would map x to w transpose. One way to do it would be to map x to w1 transpose x and w2 transpose x. And then f returns 2 parameters or something like this. Yeah, you can do it. I've just never seen it worked out, except in the one instance of multinomial. Okay. I mean, the main point of this is that I want to be able to refer to likelihoods. So I don't expect it'll be a very difficult, but I don't think this stuff is actually very difficult. I think if you review it, it's nothing magical going on. Okay. All right, so we have 2 minutes left. Are there any more? I'll post these slides. Are there any more questions you can answer for the test?
For the random forest, I vaguely remember something about the trees individually having to be high bias.
Yeah, so in random forest, we like to use really deep trees. That's right.
So there was nothing about.
Well, yeah, and deep trees are low bias, high variance. Yeah, so the idea is that when you do bagging, you're reducing the variance. So if you start with low bias, even if it's high variance, that's okay, because bagging is going to reduce the variance. Speaking of which, this leads into why might we suspect that the random subsampling of features that we use in random forest might help things.
Some will be very correlated.
Well, you don't want the tree. You want the trees to be as uncorrelated as possible. So when we have this, when I made that claim that averaging a bunch of things reduces the variance, that's true exactly when the Fs are uncorrelated. But in bagging, they're not really uncorrelated. That's why this is not really a proof.
But in one tree, you want the features to be correlated. And between two trees, you want the features in each of them to be.
Well, I think we don't really care at the feature level. We care about the final prediction level. We want the predictions between the trees to be as uncorrelated as possible, to be diverse, and we hope that by randomly selecting features on the path when we generate the random forest, we're going to have a more diverse, a less correlated set of trees that we're averaging together. Cool. So I guess we'll end now. It's 8. I'm here for questions for an hour, but I know a lot of you guys have to go. But there will be one more example along the lines of the conditional probability models that'll be in these slides that I'll post. So, cool. Yes?